Okay, so thank you, Doc Paul, and good morning, everyone. Dr. Reyna Reyes, good morning, and everyone here in Zoom and everyone watching live stream. So again, apologies for some delay because of the technical issue in the Zoom, but I think we're going on now. So I would like to introduce our second speaker, and also she's also play a big role in organizing this webinar. So Miss Angeline Macasinag, also known as Miss Angie, is an astrobiologist whose work focuses on understanding how adapts to extreme environments and what this means for the origin of life and its potential beyond Earth. She earned her master's degree in biology of extreme environment, astrobiology, at the Università degli Studi di Napoli Federico II in Italy through the Philippine Space Agency's Ad Astra Scholarship Program. DOST scholar and biology graduate of Bulacan State University, she also holds a graduate diploma in astronomy from Rizal Technological University. And Miss Angie has also managed national health R&D projects at the DOST Philippine Council for Health Research and Development and now serves as Secretary of PSBios, helping strengthen the country's space life sciences community. Her research on pigment-producing bacteria in Mars-like conditions provides insight into habitability, biosignatures, and microbial survival in space. So let's join together to welcome our second speaker again, Miss Angeline Maxina. Please give her a round of applause.
A round of applause po. Thank you.
Yan, magandang umaga po sa lahat. Ako na naman po ito. Sana hindi pa po kayo nagsasawa sa akin. So, today I want to take you on a little adventure, a journey into the future of Mars. So my talk is called The First Gardeners of Mars, an ecological approach to terraforming. This idea actually started as a class project that I worked on with a very dear friend from Vermont, USA. Her name is Savannah Zigic. So shout out to you, Savannah, if you managed to tune in. So we came up with this project during our planetary habitability course in Italy at about a year ago. So now, when you hear the first Gardeners of Mars, you might be thinking Matt Damon in the film The Martian, planting potatoes in space. But nope, that's not going to be the story that I'm here to tell. The gardener that I'm talking about is way smaller, so small in fact that you're gonna need a microscope to see them. And I'm talking about microbes, the tiny little gardeners that could one day help us transform Mars into something that is alive, green, and maybe even more like our home planet. So think of microbes as tiny pioneers with superpowers. So in the soil, they don't just sit around. They regulate climate, they recycle nutrients, they boost plant growth, they help plants handle stress, they keep pests and disease in check, and they even clean up pollution. So in other words, they are nature's hidden multitaskers. So ang dami nilang ginagawa. You've probably heard the word terraforming before, especially when people talk about Mars. So considering we have a lot of students in the audience, here's a simple definition. Terraforming means transforming the red planet so it feels more like home, the Earth. So imagine giving it air you can breathe, water you can drink, and temperatures that won't freeze your eyebrows off. So basically, it's just like turning Mars from a giant cosmic freezer into a living, breathing garden where people and plants could thrive right onto the surface without ever needing for bulky Martian suits. So, how on earth, literally, are we going to do that terraforming? So, well, in nature, here on Earth, we already have a recipe for that, and it's called primary succession. So, imagine a place where life is starting from scratch, like, for example, a land that is freshly uncovered from glacier melts, for example. So at first, it looks barren and lifeless. But then the tiniest pioneers, our microbial friends, arrived on the land. They get to work, they break down rock, creating nutrients, and quietly preparing the soil so that plants can eventually take root. So step by step, this empty landscape transforms until it becomes what we call a climax community, which is a stable, thriving ecosystem full of life. Now, here's the exciting part. Mars today is also barren and lifeless, just like those fresh landscapes on the Earth. So maybe, just maybe, we can borrow this same natural principle and one day help Mars grow into something that looks a little more like home. Now, let's take a closer look at the big question. Why does Mars need terraforming? So I posted here a short question, what's wrong with Mars? Well, technically, nothing is wrong with Mars. It's just perfectly happy minding its own business orbiting around the sun. But if we want to live there someday, there are some big challenges that we are going to face. First, here on Earth, we've got a protective magnetic field that shields us from harmful solar and cosmic radiation. And Mars doesn't have this protective magnetic field. So if you're standing on its surface, you're basically just getting blasted by cosmic rays and solar rays. So this is not going to be ideal for long-term survival. Second is that Mars has weaker gravity, which makes it hard to hold on to an atmosphere. So this results to a very thin atmosphere and extremely low pressure. So imagine a balloon that is fully inflated. That's going to be the Earth. And imagine a balloon that is basically flat. That's Mars in terms of surface pressure, atmospheric pressure. Third is that Mars has no active tectonic plates. So on Earth, plate movements recycle nutrients and keeps ecosystems thriving. On Mars, that recycling is shut off. And finally, Mars is cold, really cold. We're talking about average temperatures of minus negative 60 degrees Celsius, and it can go around as low as minus 140 degrees on its poles. So, in other words, imagine you step out onto the surface of Mars without a Martian suit, spacesuits, without any protection. You cannot breathe, you're hit by radiation, the water in your body would start to boil away, and then you'd freeze solid. So that's not going to be an exactly dream vacation for you. And if we zoom in on the Martian soil, or more accurately termed the regolith, we hit another problem for life. It's not rich, earthy soil like the kind of soil that that you plant your tomatoes here on Earth. Instead, it doesn't have nutrients that plants actually need. And to make matters worse, it's even loaded with toxic compounds like perchlorates. So all of those challenges bring us to the heart of today's talk, the terraforming project itself. But before we dive in, just a quick note that if you see this icon pop up on my slides, I kindly ask you to please don't take pictures or screenshots because we are currently, the work of this paper is currently in progress and we're actually planning to submit it for publication very soon. So I'd really appreciate your cooperation in respecting that. All right, here we go. So the big idea behind this study is simple. So we want to let microbes do on Mars what what they have been doing on Earth for billions of years. So just like in primary succession here on Earth, tough little pioneers like, for example, extremophilic microbes and lichens would be the first to move in, preparing the ground and setting the stage for more complex life. So think of them as Mars' tiny construction crew. They are slowly changing the atmosphere to warm up the planet, and they also clean up the toxic regolith so that one day it could actually become soil where plants can grow. Now, for the students in the audience, you're going to hear the word lichen a lot in this talk, so let's make sure that you know what they are. Lichens are basically a partnership of fungus and photosynthetic body. like an alga, for example. So think of them as an inseparable duo. If you take one away, the whole team falls apart. And here on the right, you can see a cross section. So you can see how the fungi and the algae work together. Yeah. Okay. So what's cool is that lichens are everywhere. Here's a photo that I personally snapped during when I was randomly walking around the neighborhood of Reykjavik in Iceland when I attended a conference. So the bright orange paint-like stuff on trees you're seeing there on the bark of the tree is actually lichen. And then here's another picture of my friend, Lara. So it's somewhere around Rome. We were roaming around Rome in Italy. And right on the wall where she is are also lichens. So they are paint-like patches that is holding on tight onto the wall. And of course, in the Philippines, we've got incredible lichen biodiversity too. So here are some photos from Luzon showing how lichens don't just look like flat splashes of paint, but instead, depending on the type, they can look crusty, leafy, or even branch-like that is uniquely adapted to its environment. And also, here's the kicker. They are not just common. They are also tough, really tough, that they can even live in deserts, even on bare rocks, even in Arctic environment. So up to the most extreme environments on Earth. Adding to that, scientists have even tested them in space, which actually exposed them to real outer space conditions. And guess what? Yes, they survived. So these little life forms are practically superheroes. Going back to the project, we've divided the whole approach into phases, which I will walk you through one by one. So phase 0 is the preparatory phase. So this is all about site selection. Basically, where on Mars do we want to start building our future? So here's a map of the planet showing the 4 quadrants that we've identified. So we have identified one near the North Pole, one near the South Pole, one along the equator, and somewhere in between. Phase 1 is all about localized warming. So before we can even think about sending microbes to Mars, we need to make it a little less frozen and a little more comfortable for life. So this means relying first on technology to kind of precondition the planet. So we've gathered some smart proposals from scientists on how to do this. One idea is to place giant orbital mirrors around Mars to direct sunlight onto the surface. So think of it like using massive cosmic magnifying glass to gently warm up the planet. So by focusing sunlight, we could melt frozen CO2 and water and then release them into the atmosphere. So in other words, the mirrors could act like the starter switch of a greenhouse, which can jumpstart the Mars climate so it's ready for the first seeds of life. Next is the installation of dome composed of aerogel. So it is a super lightweight material that is ideal for transportation as it does not consume much on the weight of the payload. So aside from being light, it also offers a good protection against the harmful radiation on the surface of Mars. So this aerogel dome will be the home of our photosynthetic microbes, in which we will see later. Next is we add something called super greenhouse gases to the Mars atmosphere. So on Earth, we usually think of greenhouse gases as a bad thing because they trap heat and make climate change worse. But on Mars, that heat trapping effect could actually be useful. So by adding these gases, these create an extra atmospheric blanket to help speed up the warming process. So all of these 3 technologies that I mentioned are just examples. So there are other more clever ways proposed by many scientists to heat up Mars. So once Mars is a little less frozen and we've already managed to build an extra atmospheric layer, it's time to get to the heart of our project, which is a draft design of a self-sustaining microbial consortium. So what does that mean? Think of it like a community of microbes grouped into chambers, indicated by the numbers here on the figure. So each chamber has a specific job, and here's the clever part. The waste or the byproduct of one chamber becomes food or fuel for another. So in other words, nothing is wasted because, and then the system feeds itself. That's why it's self-sustaining. Okay. If you look at the illustration, you'll see the color-coded arrows with the legend on the bottom part, showing which molecules are produced and which ones get passed along. So again, I apologize for putting the watermarks in the figure. I hope they don't distract you too much, and please remember to respect the little no photo icon on the side. So our diagram is divided into two sections. On top, you've got the Martian surface, and here's what it actually looks like thanks to NASA's images. This is where our photosynthetic microbes would live, protected under an aerogel that I have mentioned during the phase one that we're going to install. So obviously, photosynthesizers need sunlight in order to survive. So the surface is their place to shine. Below that is the subsurface. So basically everything under the ground where life doesn't need direct sunlight. So to give you a real world comparison, here's a photo from Hawaii's lava tubes, which look a lot like the lava tubes we know exist on Mars. So in this subsurface zone, we've placed specialized bacteria designed to clean up toxic perchlorates in the soil or in the regolith and process the sulfates. And in the very bottom chamber, we have methanogens, or the microbes that produce methane as a byproduct. So that methane would escape into the atmosphere and act as a greenhouse gas that help us to warm Mars even further. So together, this community of microbes acts like a tiny, well-organized city working as a team to slowly transform Mars into a more hospitable world. Once Mars has become a little more life-friendly, thanks to the technology and microbes that we implement from the phases 1 and 2, it's time to bring in our next pioneers, lichens. So the idea of seeding Mars with lichens was first suggested by a scientist named Armstrong. So the plan is pretty technical, but if you're curious, I've included their paper in the references. But for now, let me show you a simple illustration that we made based on his idea. So why lichens? Remember, lichens are a partnership between fungi and a photosynthetic body like algae or cyanobacteria. So together, they are super tough. They can break down rocks physically and chemically. The fungi release special chemicals that help weather or break down the rocks. And the algae or the cyanobacteria pull carbon dioxide from the air or from the atmosphere of Mars and give back oxygen into the atmosphere. So in other words, lichens can help shape Mars' surface and add oxygen into the atmosphere, thus preparing the ground for even more complex life. And finally, the final phase of our project is full-scale global implementation. So that means we take the same steps from phases 1 and 3 and then repeat them across different parts of Mars until lichens begin to spread planet-wide. So once our pioneer species have done their job, the microbes and the lichens, we could move on to the next wave, which is introducing simple plants like mosses. And then eventually we can add more complex plants like trees. So step by step, the red planet could slowly turn green, or maybe one day resembling even Earth itself. So to summarize everything that I have said, terraforming Mars means turning it into an Earth-like habitable world. So just as life on Earth slowly colonizes barren places through primary succession, we can imagine using the same microbes and lichens to kickstart similar processes on Mars, transforming rock into soil and shaping the atmosphere. And of course, this is not going to be an easy task. It will take both powerful technology, resilient biology, and it will be long, resource-heavy journey. But step by step, the dream of making Mars a living planet could move closer to reality. And here are the references that I use. If you're interested to deep dive into this idea, you can screenshot this and do some more readings. And that would be all if you're interested. And if ever you have questions related to this na hindi ma-address during the Q&A, you can send me an email here. So yeah, we can brainstorm. Thank you.
All right. So thank you so much to that, Miss Angie. No. Thank you for a big round of applause to Miss Angie, please, everyone. Big round of applause to Miss Angie, our very own secretary for the Philippine Space Biosciences Society.